Hello and welcome to the video lecture series on chapter 6.1 in the Log 5 textbook. Excuse me. We're going to be looking at inference with a single proportion in 6.1. And again, we've been looking at single proportions for a while now. The main difference with chapter 6 is we're no longer going to use the bootstrapping techniques we used in chapters 3 and 4. So what we're going to do is first look at a standard error formula for a sample proportion. We're going to look at necessary sample size for the central limit theorem. Kind of go over that central limit theorem again for sample proportions. Then look at confidence intervals, how to construct confidence intervals for a single proportion. This second from the bottom bullet point is new, how to figure out sample size. If we want to get a big enough sample size for a particular margin of error. And then lastly, we're going to look at hypothesis testing for a single proportion. All right, so the standard error formula for a single proportion is given by this. We take the square root of p times 1 minus p over n. And where this comes from actually involves a little bit of calculus and some linear algebra. So I would say the mathematical level is higher than the prereqs for this class, so I'm not going to show how we come up with this formula. But if you've taken a calculus, or really a couple semesters of calculus, it's not too terribly difficult to come up with this formula. But since that's not a prereq for this class, we're going to kind of take this for granted. And one thing you want to notice is here we've got a population proportion parameter p times 1 minus p and n. So the idea goes the larger the sample size, if you remember from a previous math class, if your denominator gets bigger, the whole thing gets smaller. I think if you have like 10 over 10 is 1, and 10 over 1,000 is a very small number. So that idea is going to continue. If you have a big sample size, your confidence interval is going to get smaller, as is your standard error. All right, let's look at an example. In the 2010 U.S. Census reports that of all the nation's occupied housing units, 65.1% are owned by the occupants. So that would be about 35% or so are rentals. All right, if we were to take a random sample of 100 homes, what would the standard error of p-hat, the sample proportions, be? So we're going to go to this previous standard error formula. And as I said before, this p is for population parameter, population proportion. And for own homes, if we're dealing with the census, we assume that p is 65.1%. So when we go to that formula, standard error is the square root of p times 1 minus p over n. We plug in p as 0.651 times 1 minus 0.651 all over 100. Then you take the square root at the very end to get 0.048, round that to 3 decimals. So I want to look at this kind of going back to how we calculated standard error in chapters 3 and 4. And see, we should get a similar standard error. This is chapter 6 is the classical method, the formula method. These were used before we all had easy access to fast computers and calculators. So I want to go to StatKey and look at, say we're doing a confidence interval for a single proportion. It's a little bit bigger. And that last one, we had a sample size of 100. The count was 65.1. If I click OK, I'm going to get an error because StatKey, you can only allow a whole number. So let's just assume it's 65 out of 100. So it's not the exact same scenario, but 65 out of 100. Whereas over here, we're looking at 65.1%. And then if we generate a whole bunch of samples, notice right here, this is your standard error. I got about 0.049. I'm going to go through, but this would change if I keep doing more samples. 0.048, So it's not the exact same necessarily, but the bootstrap method we covered in chapters 3 and 4 should match up very similarly with the formula method from chapter 6. All right, here's just another visual showing that 0.651 or so should be about the center and that standard error. All right, so I want to look at the distribution of sample proportions. And here I have some static pictures. I'm going to go to stat key in just a moment. But if we take the proportion to be 0.5, so think about flipping a coin. If you only flip a coin, one coin is your sample, right? You could get heads or tails, and that's equally likely. But let's suppose you flip 10 coins. And after you flip 10 coins, you keep track of how many heads and tails. So notice you've got the largest possibility is to get half, 5 heads and 5 tails. But you could possibly get, 7 or 8 heads out of 10, or 7 or 8 tails, and maybe even possibly 10 heads, although it's very unlikely. But we have this kind of normally shaped distribution, kind of. Getting there. Now, if we flip a coin 30 times and we plot the sampling distribution, we should end up with something even more normal-like. Notice here we have, space between the bars and whatnot. Here it looks like we're getting to that normal curve. And if we flip 100 coins, then here notice we get a little bit more normal. 50 coins right here, and then 100 coins, a little more normal. And notice what's happening to these distributions. As we flip more and more coins in our samples, they get more and more compact, more narrow. Again, the idea is if you flip 10 coins, it's possible to get, say, 9 out of 10 heads. But if you flip 100 coins, it's very unlikely you're going to get 90 out of 100 heads when you flip a coin. So that's the general idea. The bigger the sample size, the larger that standard error. Now I want to look at, say we have a skewed proportion. So this could be like a coin that's weighed heavier on one side, or something, this one is more likely to happen. So, 70% of the time you get a 1, 30% of the time you get a 0. Now if you flip a coin 10 times, we're still going to have this would be a left skewed distribution, because the tail's going to the left over here, but it's getting a little bit more normal. If we take 30 times, I'd argue this is not quite normal. Again, you still have this little left tail. And then once you get to 50 and 100, now it kind of looks like that normal distribution, the bell-shaped curve. And again, notice the distributions are getting more and more compact, more narrow. And let's look at the other extreme. What if P is 0.1? So you've got, roughly a 90% chance of getting, say, a tails, but only a 10% chance of getting a heads. If we flip a coin 10 times, we're still going to much more likely to get the zeros over here. Still a right skew when we flip a coin 30 times. If we go to 50 times, I would still say this still looks like a right skew. And finally, when we get to 100, if we zoom in, we could say, okay, maybe this looks more like a normal curve. So we're going to look at how large a sample size do we need. If we want to use a normal distribution to approximate the distribution of our sample proportions, we need to make sure the sample size times proportion is at least 10, and the sample size times 1 minus the proportion is at least 10. So I'll kind of think about this as another way we need to, if we want to use a normal distribution, use the Z distribution to approximate the distribution of P hats. There has to be at least 10 successes. I kind of think of N times P is 10, and 10 failures. N times 1 minus P. So I want to look at a couple scenarios before we go on to central limit theorem. All right, so we have, for what values of P and N can we assume the distribution of P's is normal? note here, we need to have at least 10 successes. And that means in this case, n times p needs to be at least 10 and at least 10 failures. Which in that case means we take n times 1 minus p, it needs to be at least 10 in order to use normal distribution. All right, I'm going to make a different color to highlight that. So 10 successes, 10 failures. So if we just look right here, how many successes do we have? Well, that's just 1 times 0.5 equals 0.5. So since we don't have at least 10 successes, we can't use normal distribution. So if we're looking at sample size of 1, p equals 0.5, we can't use normal distribution. I'm going to look over here for sampling distribution for proportion, just to kind of look see what that means again. So we have proportion of 0.5, sample size of 1. So every time I generate a sample, that's just like flipping one coin. Just as I go, I'm only going to get 0 and 1. If I generate a bunch of samples, this is absolutely not normal. Not bell-shaped. What if we jump that sample size to 20? Well, let's look at each one. Our number of successes is going to be n times p, which in this case is 20 times 0.5, and that is 10. Okay, good. We want to make sure we have at least 10 successes, so we're good there. And then we need to see how many failures do we have. What I mean by that is take n times 1 minus p, which in this case n is 20 times 1 minus 0.5. But since it's a probability is 50%, these are going to be the same. So we can use normal distribution. As long as we have successes and failures of at least 10. And if we try to visualize that again, I still have that, the edit proportion still 50%. I'm going to change the sample size now to 20. So anytime I generate one sample here, now that's a sample of 20, right? So like 9 tails out of 20. Make another one, and 15, 9, 8, 10, 11, 12, and so on. We generate a bunch of samples at once. We get this normal-ish distribution. All right, what if we take the same sample size at 20, but now we take a population proportion of being 0.9. So successes in this case is n times p. That would be 20 times 0.9. And what is that? Throw that in your calculator. That's going to be 18, which is good. I'm going to make sure I have at least 10. But failures on this for this scenario would be equal to n times 1 minus p, which is 20 times 1 minus 0.9, which is 20 times 0.1, or 2. So we cannot use normal distribution in this case. And I want to kind of visualize why can't we use normal distribution. Same sample size as number 2, but the main difference is the proportion is 0.9, so it's going to be a much stronger skew. So I'm going to keep that 20 there, edit proportion to 0.9. Again, every time I grab a sample, it's out of 20, but these samples are going to be much more likely to be at the 90%. And if we generate a couple thousand, notice I don't really get that bell-shaped curve. I don't get the ghost curve. This is definitely left skewed. All right, here if we go to a sample size of now 100 with 9, now I get 100 times 0.9, which is 90 successes.